In Chapter 4, we begin our study of forces, and we're going to introduce all three of Newton's laws. That'll finish up this unit, but we're not going to be through with forces. We're going to go into a lot of applications in Chapter 5, so we'll definitely be continuing our study of forces for a while. Chapters 2 and 3, we studied a field called kinematics. That's basically the study of how things move. All of our constant acceleration problems and free fall problems fall into this field. What we're studying now is a field called dynamics. In dynamics, we begin the study of forces, or why things move. Up until now, we didn't worry about why something was moving, only how it moved and how it would behave. Okay? Why things move is studying forces. And a force is simply that's probably the definition that you learned in the middle school. A force is a push or a pull. But another thing about forces that's important to understand is a force always is an interaction between two objects. If I push on this eraser, there's an interaction between me and the eraser. If I drop this marker, it's because it will fall because there's an interaction between the marker and the earth. We call that a gravitational attraction. There's lots of different kinds of forces, but every force involves an interaction between two objects. Every force is felt as either something pushing or pulling an object. Some forces require direct contact. We call those contact forces. The one you're probably most familiar with is friction. Some forces can act over distances. The one you're probably most familiar with is gravity. But that's certainly not the only one. Electrostatic forces, magnetic forces, they act without actually having to touch the object. But if I want to push something, that's a contact force. And if friction opposes me, that's a contact force. We're going to need some ways of describing all these forces and labeling them all if we're going to solve problems. So let's just look at some of the more common forces and how we're going to label them and what they are. Different books will use slightly different methods of labeling. They're similar. So if you took physics before, this might look slightly different than what you've had in the past, but it shouldn't be hard. So here's some common forces. One is weight. When you get up and weigh yourself in the morning, you don't normally think of your weight being a force, but weight is actually the downward pull of gravity. It's a gravitational force. All forces are vectors, so I'll put a little arrow. We'll use a lowercase w to represent weight. We leave the little arrow off if we're just talking about the magnitude of the weight. So if we say something weighs 50 pounds, we don't have to put an arrow. Particularly on weight, everyone understands that weight is a downward force. So that is simply the force of gravity on a mass. Another force, and this one you may not be as familiar with, is the normal force. That's a lowercase n, and that is the force exerted by a surface on an object. Anytime you have something resting on a surface, you might have a book resting on a table. I have some books here. The book is pushing down on the table, but the table pushes back up. Okay, that's the normal force. The word normal in mathematics, and you might as well learn this now, is that normal, it doesn't mean average or typical or the same things that it means in everyday language. Normal means perpendicular. Anytime you're talking about something being normal and you're in geometry, mathematics, physics, normal means perpendicular. So basically, all it means is that the force, if I have a heavy book sitting on my table, the table pushes upward and the direction happens to be perpendicular to the surface. Normal forces are always perpendicular to the surface. And we'll certainly come back and talk more about normal forces. That's not going to be all you learn about them. Right now we're labeling. We know that friction, and the symbol for friction is just going to be a lowercase f, is a force that opposes motion. Opposes is a good physics word too. When we say it opposes motion, it means it points in the opposite direction. So if something is moving to the right, friction will always be to the left. Friction always opposes the motion. If you have something sliding down a ramp, then friction's going to point up the ramp. But if you have something being pushed up the ramp, friction's going to point down the ramp. It will oppose the motion. Another one we use a lot is tension. Now tension we use a capital T, which is good. We use lowercase t's for time, so it's good to have something a little different. And that is simply a pulling force exerted by a rope, cable, string, chain. There's anything, a piece of fishing line. But it's going to be like a rope, and the tension is all throughout the rope, but it exerts a pulling force. Now, there's a whole lot of other forces that where somebody's pushing a car or pulling a sled. Those are generally what we'll just call an applied force. Some person or some animal or some object pushes or pulls on something else. And for an applied force, I usually use an F with a little a, but some books will use a capital P for a push or pull. Force is pulling, they just call it a P, okay? And that's basically any other push or pull. So all we've done so far is really just name some of the more common forces that are going to show up in our problems: weight, normal force, friction, tension, an applied force or a push or a pull. Oops, it's a T. The net force. We're going to hear that phrase a lot. The net force is the sum of all the forces acting on an object. I want to emphasize the word on because it's easy to get confused about forces that are acting on an object and forces that are exerted by the object. And we want to be really clear. Most of the time when we're solving a problem, we're more interested in the forces that are acting on the object and not very interested in the forces exerted by the object. So, net force, there it is. We just write the word net. Another way you can think of that is the resulting force. And it is simply equal to a vector sum of all the forces, however many there might be. We often write it like this. The net force is equal to the sum of all the forces. If you're not familiar with that summation sign, that just means add up all the forces. It means exactly what that meant right up above it. Now, one of the things we know is that when we start adding forces, direction is very important. We might have lots of forces at all kinds of angles we need to add. And to do that, we'll need components. Any force can be replaced by its components acting at the same point. Now, for example, if we had some block and somebody had fixed the handle right here and they were pulling it with some force at some angle above the horizontal, we still measure everything from horizontal, we can certainly say, hey, you know what? I need that force in components. I need to know what that y component is, and I need to know what this x component is. And we know how to do that because we learned that back in chapter 1. The horizontal component is F cosine theta, and the vertical is F sine theta. Very, very important. If you're going to just use those formulas, you need to be sure you're measuring from the positive x-axis. If that angle's measured from the negative x-axis or the y-axis, you're not going to get the right result. So be sure to remember this is based on. Now, if you really know trig, you can maybe do things differently. But let's assume we're not experts at trig. We'll just measure all of our angles from the positive x-axis. Okay, I think I'm going to depart a little bit from the order that the book does things. They go into Newton's first law at this point. That's a great place to go, but I think what I'd rather do is let's just go ahead and practice a little bit with free body diagrams. We'll come back to them a little bit more as well. But I think it's just important as I work through things, I'm going to be drawing these probably earlier, that you know what a free body diagram is. So, 4-6 deals with free body diagrams. This is the step that students love to skip in solving problems involving forces. But it's the one step that will help you really, really understand a problem. So don't skip it. Even if at the beginning it seems too simple and you don't need it, it's kind of like algebra. If I don't know how to draw my free body diagram when the problem's really easy, later when the problem's much more complicated, I won't know how to draw my free body diagram because I didn't draw the easy ones. So we're going to start with the easy ones. Okay, the free body diagram shows all the forces acting on the object. But not the forces exerted by the object. You want to be able to draw every force that's acting on this mass, whatever it is we're interested in. But we don't care what forces that mass might be exerting on other things. We're going to draw the mass as a point. We're going to treat everything as point masses right now. That's part of that idealized model that was mentioned back in chapter 1. It's easy to treat a baseball as a point, and then we don't have to worry about the fact that baseball is actually rotating. It's easier to treat a car as a point. And for a lot of problems, it makes perfect sense, so we don't have to worry about it. We represent the object with a dot, and then we draw all of the forces that are acting on it. So, let's say, for example, my situation is an apple on a table. There's a table. Oh, look, I have red. I can draw my apple. See if I can draw an apple. There's my apple. Well, what forces are acting on this apple? And I want to point out this apple is at rest. We haven't studied Newton's first law yet, but it makes sense that this apple's at rest. The total forces on it are 0. That's what Newton's first law is going to teach us. So we look at it and we go, okay, here's the apple. What forces would be acting on it? Well, one force that acts on everything here on Earth is gravity. Everything weighs something. So the weight of the apple is pulling it down towards the center of the earth, but the apple's not moving. If the apple's not moving, there has to be another force to balance it. When something's at rest, and we'll just talk about at rest right now while we do these free body diagrams, all the forces are balanced. The other force is the normal force. Since the apple is pressing down on the table pushes back. It pushes back with a perpendicular force we call the normal force. Now, I should try to draw these where the vectors are the right length, the right direction. They don't have to be perfect. But in this case, I know that the total force is 0. So I want to draw a vector down for the weight, a vector up for the normal force, and I know they should be equal. If this apple weighed 1 Newton, then I would know the normal force was 1 Newton. Okay. All right, so that's a pretty easy free body diagram. So easy, students don't ever want to draw it. Let's draw something else. Suppose I tell you that I have a wagon being pulled across the ground. And a wagon being pulled across the ground might look something like this. Here's some wheels. Here's the handle. This is some applied push or pull. I'll call it a pull. And there it is. Now, so this is let me change my title here. The wagon being pulled. And we're not even going to go into whether it's being pulled at a constant speed, whether it's accelerating, whether it's slowing down. Let's say I don't know any of that, but I can at least look at what are the different forces that are acting on it. So I let the wagon be a point. I know the wagon weighs something. So it has a downward weight. I also know there has to be a normal force. Now, in this case, the normal force may not equal the weight. I'll explain that later, but I know that I have the weight, and I know that the wagon's pushing on the ground, sidewalk, road, so it's pushing back. I also have this push or pull. This is a pull in this case. And I want to, there's beta. And then finally, unless this is an unusual situation, I have some friction. Chances are this wagon, I have to pull with a little force to overcome friction. Now, we always put our mass, our object, at the origin. Okay. We can decide which way to let our x and y axes go later. There are times, like when we're working with things that are on ramps, that we realize it makes more sense to let our x, y be at a bit of an angle. But in this case, this force, and this force are all perpendicular, so it makes sense to think of this as being the x-axis and this being the y-axis. Okay? Now, when I get ready to solve this problem, I'm probably going to take this force and break it into components, but not when I draw my free body diagram. My free body diagram should show all the forces, show what direction they point. So in this case, there's 1, 2, 3, 4 forces. 3 of them happen to lie on an axis. 1 of them does not, but that's a free body diagram. Okay, so now that we've talked just a little bit about free body diagrams, we're going to come back to them later. But I just think it would help me as we worked through problems. So, jumping back to Newton's first law. first law is often called the law of inertia. Now, it might surprise you that Newton didn't discover, nobody can invent these laws, these are laws of nature, but he didn't actually discover the law of inertia. That was discovered by Galileo. Galileo was the first person to realize that it would not require a force for something to remain at rest. Well, that seems obvious, but it also doesn't require a force for something to move at constant velocity. And that is a little surprising. That's the part that takes some getting used to. But he did an experiment with lots and lots of ramps. And what he realized at the end of his experiment was if he could get rid of all of the friction, that something in motion would continue to move at a constant speed. Think about it like this. Here's what he did. He said, you know, if he set up a ramp like this, and he let some marbles or something roll down, when it was rolling down, the speed increases, or the velocity increases. And when it's rolling up, the speed decreases. And as he used smoother surfaces, he realized this came closer and closer to being a constant speed. And what he came to the conclusion was, if the speed will always increase rolling down, that's because gravity accelerates. And if it always increases going up, that's because gravity causes it to slow down. Then really on a level surface, if there was no opposing force, if he could eliminate friction, it would move at a constant speed. Okay, I say all that because I just want to give Galileo some credit. Isaac Newton also gave Galileo credit. He said, and I'm going to not quote him perfectly, "If I have seen farther than other men, it's because I stood on the shoulders of giants." He knew that he relied on discoveries by people that went before him. But what he did is he said, you know, if I take this thing that Galileo discovered and tie in when he did universal gravity, this that Kepler discovered, if I synthesize this information, I can explain motion in 3 laws. This is the first one. Every object continues continues either at rest or in constant motion in a straight line constant motion in a straight line. I'm just going to put in a, that's a fancy way of saying constant velocity. Unless it is forced to change that state by forces acting on it. Every object continues either at rest or in constant motion in a straight line unless it is forced to change that state by forces acting on it. A lot of times you learned this in middle school. An object in motion tends to stay in motion, an object in rest tends to stay at rest unless there's an unbalanced force. That's really a simpler way. If there is an unbalanced force, then motion changes. If the forces are balanced, which is a fancy way of saying if the net force is 0, the motion continues. So, a better, maybe simpler way of saying this would be something like this. An object with no net force acting on it moves with constant velocity Now, when I say constant velocity, I'm going to put in, which could be 0. We can think of something being at rest as having a constant velocity of 0. So, an object with no net force acting on it moves with constant velocity and thus has 0 acceleration. In other words, if the net force is equal to 0, the acceleration is equal to 0. Or, if the acceleration is equal to 0, then F net is equal to 0. That's what Newton's first law tells us. If the net force is 0, there's no acceleration. If you don't have any acceleration, there's only 2 possibilities. One, you're at rest. That's the obvious one. The other is that you are moving with a constant velocity. You are moving with a constant speed in a straight line. Okay? That one goes against our intuition. Whenever we see something moving, it naturally seems to slow down. If I try to slide something across this table, like this calculator, it only slides for a little bit and then it stops. It stops because there's an opposing force. There is a force acting on it. What force is acting on it when it slides across? Friction. Remember, friction opposes motion. So we often see that it looks like there's nothing acting on it and it's slowing down. But if we stop and think, there is something acting on it, and it's friction. If we can get someplace where there's no friction, no air resistance, like outer space, then you could fire a rocket. And as long as it stayed far away from anything, other planets, other meteorites, stars, asteroids, whatever, it would just move in a perfectly straight line at a constant speed. That's just a situation that's really hard to create here on Earth. We use the word equilibrium when we want to describe something that has no net force. Another way to say that is the sum of all the forces is 0. Now, doesn't mean there aren't forces acting on it. There can be lots and lots of forces acting on something, but if all of those forces add up to be equal to 0, you're in a state of equilibrium. If something's in static equilibrium, I use EQ for equilibrium because it's a long word. Basically, that just means it's at rest and the net force is 0. if we talk about something in dynamic equilibrium, we usually mean it's moving. That would be moving at constant velocity. And we know that also would mean that the net force is equal to 0. Now, a lot of problems in physics don't take place in a straight line. In Chapter 3, we saw that with circular motion and projectile motion. So what we have to be able to do is realize that when something is in equilibrium, not only is the net force 0, but the sum of all the forces in the x direction, all the components have to equal 0, and the sum of all the y components would also have to equal 0. A lot of times this is the approach we have to take when we're actually ready to solve a problem. The thing I want you to really carry away is Newton's first law applies any time the net force is 0, or any time you have a problem that says the object is at rest. Well, by golly, if it's at rest, I know I can add up all the forces and they equal 0. Or it says something like the object was like an elevator moving up at a constant speed. Well, I know elevators travel in straight lines. A straight line at a constant speed is a constant velocity. The net force is 0. So anytime I see constant speed in a straight line or at rest, I know the velocity is constant, the net force is 0. No acceleration. Now, we describe how difficult, we call this the law of inertia. Why do we call it the law of inertia? Well, some objects are easy to start in motion, and some objects are very difficult to start in motion or to change their motion at all. Some objects, when they're at rest, they really want to stay at rest. And some objects, when they're moving, they really want to keep moving. So how would we describe that? Well, let's think about a ping pong ball and a bowling ball. If I had a ping pong ball and a bowling ball sitting on this table, and I thumped them both, the ping pong ball would go flying. Chances are the bowling ball would just sit there and my finger would hurt a little bit. What's the big difference? Why did this bowling ball have so much inertia and want to stay still, really resist changing its motion, but the ping pong ball didn't? Or suppose somebody threw a ping pong ball at me and somebody threw a bowling ball at me. Which one's going to be easier to stop? Obviously the ping pong ball. It's really easy to change the motion on a ping pong ball. It's hard to do it on a bowling ball. I could say the same thing about a toy car and a Mack truck. It's really easy to push a toy car, almost impossible to push a Mack truck. What's the difference? Well, you don't have to think very long before somebody's out there screaming, one is heavy, one is heavy. Things that are heavy have a lot of inertia, but it's not actually the weight, it's actually the mass. Okay, so inertia is the tendency of an object to stay at rest or stay in motion. If it has more inertia, it's more likely to stay at rest or to stay in motion. Mass is a measure of inertia. So, and anytime we want to put a numerical quantity on something's inertia, what the quantity we're looking for is its mass. Sometimes in physics we talk about two types of mass. There's something called the inertial mass, which is what we're talking about here. that's its tendency to resist changing its motion. And there's something else called the gravitational mass, which you might think is more closely related to what you might have learned in middle school, the amount of matter. That gravitational mass affects how Newton's law of gravity applies. But what we found out is through extensive testing, experimentation, there's no quantitative difference between inertial mass and gravitational mass. So even though we are in a sense doing two different types of experiments to measure inertial mass or to measure gravitational mass, we get the same result. So we don't have to spend a lot of time worrying about the difference. But there are two different ways to define mass, but they both give us the same number. One last topic is anytime we talk about motion, we're going to need a frame of reference. We can't talk about it without a frame of reference. Okay, well, a frame of reference that is not accelerating is called an inertial frame of reference. Newton's laws all work in an inertial frame of reference. If I'm standing still and I don't have a ball to throw up and catch, and I'm not very coordinated, but if I throw this up and I catch it a few times, even though I'm moving really fast with the sun, so is this marker. So I throw it up and it obeys Newton's law. However, think about something like a ball sitting on an airplane. As long as the airplane moves at a constant speed, the ball that's sitting there at rest remains at rest. It seems to obey Newton's law. But if the airplane begins to accelerate, the ball will appear to spontaneously roll to the back of the plane. There's no force acting on the ball. In fact, it tends to roll back because of its own inertia. So what's going on? Does Newton's laws break down? And the answer is sort of. Newton's laws don't work in accelerated frames of reference. Now, the Earth is not a perfect inertial frame of reference, but it works for our purposes. We can treat the Earth as if it is still. That means any other frame of reference that moves with a constant velocity relative to the Earth is also a perfectly good inertial frame of reference. The only thing that will ever give us trouble is an accelerating frame of reference, so we won't do problems with accelerating frames of reference. But I did want you to know what an inertial frame of reference was. Okay, now let's think a minute. I'm going to say, I kind of want to do this problem. I'm kind of jumping back and forth from my notes, but I'm going to go ahead and work a problem that involves Newton's first law. Maybe I'll just make up a different problem. Suppose I have a big cable, and hanging from this big cable I have a big mass. This big mass weighs 500 newtons. If I said draw a free body diagram, this object is at rest, there'd be two forces. One is the weight, points down. And they told me what it weighs. It weighs 500 newtons. The question that might be asked is, what's the tension in the cable? Well, the cable is the other force. The reason that this 500 newton force is remaining at rest is because I know the net force is balanced. The tension in the cable would point upward. This represents whatever this big heavy thing is. I'd say 500 newtons is about 50 kilograms. something that weighs around 110 pounds. That's all I know. So, what would this be? It'd have to be 500 newtons. Why do I know it's 500 newtons? Because of Newton's first law. If an object is at rest, all the forces are balanced. So if the weight is pulling down 500 newtons, then the tension, that upward pull of the cable, has to be 500 newtons. And a free body diagram makes that really obvious. Okay, so on that, let's move on to Newton's second law. Newton's second law doesn't require a lot of words. It's best stated as an equation. I'm going to talk till I'm hoarse today. It says, that the net force is equal to the mass times the acceleration. That's it. The net force equals the mass times acceleration. Another way of thinking about it is how much something accelerates is directly proportional to the force. If I rearrange this a little bit, this will also make good sense. Sometimes we see it written like this. The larger the force, the greater the acceleration. The acceleration is directly proportional to the force. The greater the mass, the smaller this acceleration. That also makes a lot of sense. The acceleration is inversely proportional to the mass, or the inertia. As this inertia gets larger, it's going to take more and more force to create that same acceleration. Okay? Now, we need some units. Well, a couple of things. First of all, you need to remember force is, in fact, a vector quantity. And if I haven't mentioned that, I feel certain I've mentioned it. I've drawn diagrams. We measure force in newtons. That's the SI unit. There is a direction. The acceleration is in the direction of the net force. That makes perfectly good sense. The net force is going to determine not only the size of the acceleration, but the direction of the acceleration. If we look at this gives us some indication of what a newton has to be. We call this unit for net force a newton, but we know mass is measured in kilograms, and acceleration is measured in meters per second squared. So we now know that 1 newton is actually 1 kilogram meter per second squared. This is what we call a derived unit. These are fundamental units, kilograms, meters, seconds, and this is that combination, or derived unit. It's just easier to talk about force being in newtons, and it's going to be measuring all the time as kilogram meters per second squared. When we get ready to solve problems, we'll probably have to break most of our problems down into components. When we do that, we're going to realize that the sum of all the forces in the x direction, that's the net force in the x direction, is going to be mass times acceleration in the x direction, and that the sum of all the forces in the y direction gives us mass times acceleration in the y direction. Through most of this course, we're going to find that if we want to solve problems in two-dimensional, we just break everything into horizontal and vertical components. You could do the same thing in 3 dimensions, and then we'd have that z component, that third component. Let's do a couple of examples. A worker in spiked shoes pushes a 40-kilogram box with a force of 20 newtons across a frictionless floor. What is the acceleration of the box? So here's the floor, here's a box, there's somebody back here pushing on the box, really long arms. Let's draw a three-body diagram because that's the answer. And while we're answering questions, here's one more question. Why the spiked shoes? Well, if the floor was truly frictionless, he couldn't push it if he didn't have any friction. He'd just slide backwards. So he needs to be able to push it. So they gave him spiked shoes. So here's the box. What are all the forces that are acting on this box? Well, it has weight. We haven't talked about how to find its weight yet, but we do know its mass, so we'll learn how to do that soon. And there's a normal force. And it doesn't accelerate vertically, so we know those two are equal. We know the sum of all the forces in the y direction is 0, so we're not really very worried about that. The normal force and the weight are going to exactly cancel out. But he's pushing it with a force of 20 newtons. So we have this other force, 20 newtons. Those are the only forces in the problem. So that's obviously 0. There's obviously no acceleration that way. But if we look at the forces in the x direction, there's a 20 newton force. I have a mass of 40 kilograms times the acceleration. So that's just going to be 0.5 meters per second squared. Piece of cake. F equals ma. We know the force, we know the mass, we can find the acceleration. We could even make the problem a little more complicated. What if they said there was a frictional force? What if they said the frictional force was 10 newtons? If they told me I had a frictional force of 10 newtons, then when I get my net force in the x direction, it wouldn't be 20 newtons. It has a positive 20 and a negative 10. My net force would be a positive 10. And this time my acceleration would be about 0.25 meters per second squared. I have to be kind of careful. I don't really have two significant digits, but I'm going to keep that for right now. I just kind of wanted to show you how it would be possible to introduce another force. Let's do another one. A waitress fills a ketchup bottle. Giving it a velocity of 2.8 meters per second. If the bottle has a mass of 0.20 kilograms and it stops after 1.0 meters, find the frictional force. Oh my goodness, I think I just mixed up everything we've learned so far this year. I've got velocity, I've got mass, I've got it stopping, I've got forces. I definitely want to draw probably a couple of pictures. First of all, if I let this be where this waitress gave it a shove, here's my bottle of ketchup. I don't know what a bottle of ketchup looks like, but there it is. Bottle of ketchup. And it slides. She pushes it, and it leaves with some initial velocity, 2.8 meters per second. It slides over here to 1 meter, and by the time it gets here, it has a velocity of 0. From my kinematics, I know the displacement, I know the initial velocity, I know the final velocity. I think the piece of the puzzle that I'm going to want to get from that is acceleration. Over here, let's draw the free body diagram because I'm interested in this frictional force. Once she gives it a push, this is after she lets go of it. I know the weight of the ketchup bottle is down. I know the counter pushes up with a normal force. And I know that if the object is moving to the right, then my frictional force must be to the left. That's my free body diagram. These two, once again, are vertical. We don't have any vertical motion. Vertically, we're essentially at rest. So the interesting part of the problem is the horizontal motion, which tells me that the net force equals mass times acceleration. And in this case, since these two cancel out completely, the net force is going to be the friction. The frictional force simply equals the mass times the acceleration. I know the mass, I don't know the acceleration. But I did chapters 2 and 3, chapter 2, we're going to assume that this is a constant acceleration problem and we can figure out what the acceleration is. We have a formula that says v squared equal v0 squared plus 2a delta x times the displacement. That's the one that says if you don't know the time, you don't need the time, you can do this. The final velocity was 0. So this is 2.8 squared plus the displacement, that's 1 meter. So I put in 1 meter. So I just get plus 2a. When I solve for a, it's going to be negative. Let me put that in my calculator. 2.8 squared divided by 2, 3.92, negative 3.92 meters per second squared. They didn't ask for the acceleration, but that's what I got. That means my frictional force is mass times acceleration, so 0.20 kilograms, negative 3.92 meters per second squared. And I get a negative point. We really only have two significant digits, so I'm going to keep 278 newtons. Now, all the negative means is that it's opposite the velocity. Since we said the velocity was positive, then the friction force is negative. It points in the opposite direction. Oops, and I'm off by something. I'm off by a lot. Or else I'm off in my notes. Let me look here. Oh, I'm not off by a lot. I'm perfectly fine. There's an error in my notes. I left off a decimal. Okay, so I think that's a good place to stop for this video. We still want to talk about the relationship between mass and weight, and we want to talk about Newton's third law. So we'll do that in our second part.